In this video, we will be talking about mathematical combinations, which, very similar to permutations, is a way of taking a bunch of objects and selecting groups of those objects in a particular way. Let's go ahead and read the definition. It says a selection of R objects without regard to order and without repetition, selected from n distinct objects is called a combination of n objects taken R at a time. So often people will say NCR or n choose R for a way of describing what a combination is. And notice that the difference here is that the order is irrelevant. So it's a different type of question than a permutation question, and that's always the thing I recommend when you start with these sort of questions in the in the homework. Make sure, well, obviously the chapter that it's in will probably be a hint as to what it is. But just think about, does the order of these objects matter or not? So let's look at example number 6. It says a class consists of 26 students. The teacher selects 3 students at random to participate in an activity. How many different groups could the teacher select? So this one is really similar to the example we did in a couple videos ago, which was the class had 26 students, and then the teacher was selecting a secretary, a president, and a mascot, which we already have solved the answer to. But here, they're picking 3 students, and they're not like being put into specific positions, which is a little bit different. So a way I could think about a permutation is I have these boxes, and the teacher is placing one student in one box, a different student in another box, and a third student in a third box, where those boxes are individual different things. Here, it's not really like boxes. It's like it's a larger group of 3 students, and the teacher's trying to pick 3 people to go in the group. But if I think about the groups here, like trying to compare the event space from that example, for example, ABC versus, whoops, let's just say I was taking the students ABC for my group. The question is that different than BAC? Because in the previous example, right, where they were selecting president, student secretary, and mascot, those were different groups. Because here, what that means is, well, student A is president, student B is secretary, student C is a mascot. But in BAC, it's different, right? Because student B is president, student A is secretary, and C is a mascot. So in either case, C was the mascot, but A and B are switched. They're switched positions, which means they have different jobs, that those are different outcomes. But in this example, these are not really different outcomes, because in each case, this is just a group of the students. Like imagine that they're all working together, or they're up at the front of the class participating in whatever crazy activity the professor has planned. But it doesn't really matter the order I select them when I'm selecting groups of them. Now, if one of these students represented the team leader, then it might be considered different, but in the context, these are not different. So basically, the math is going to be a little bit different in this case. And basically, it would represent by a combination. So in this case, we'd write this as 26C3 because we're going to be choosing 3 students out of 26. Again, in a group where order does not matter. So instead of thinking picking and choosing, to me, I don't think that those monikers really help understand the difference. I kind of think about the difference as when I'm using the permutation, order is important. The arrangement of them matters. When I'm using C for combination, the order does not matter, where, like in this context. So mathematically speaking, let's go ahead and use some of these formulas just to try to understand how to do this. Because if I was trying to set this up using basic fundamental counting principle logic, I might have a little bit of trouble knowing how to adjust for when the order doesn't matter. But what the formula says is that we should take n factorial, 26 factorial, and divide it by r factorial times n minus r factorial. So r factorial is 3 factorial, and n minus r factorial is 23 factorial. And so if I'm comparing it, and this should give me the number of combinations of those objects. And if I'm kind of comparing this to the math I did before, where I was simplifying 26 divided by 23 factorial, that reduced to just 26 times 25 times 24. Or really, actually, notice that really this is NPR. So if I think about this a little bit differently, one way that you could write NCR, oops, let me use lowercase n there, Oops, you can't see what I'm writing. NCR is equal to NPR divided by R factorial. And just notice that, and we're going to get to why, and I'm going to try to explain why this makes sense in a minute. But like if I'm looking at this formula, n over n minus r factorial, that is NPR. So basically, if I take NPR and divide it by r factorial, that's going to leave me with NCR. Or as another box from the book has it, it says NPR is equal to NCR times r factorial. Notice if I multiply across, right, that would be r factorial times NCR would leave me with NPR, which is consistent to right there. But that's just something I wanted you to notice. But like also with all of that being said, one second, let me highlight this. This is just NPR. And I could always simplify that components because that's the point, right? It always simplifies down to a chain of factorials, as I was saying before. That would make, well, 26, whoops, I don't want highlighter. I want 26 times 25 times 24, and that's going to be divided by 3 factorial. And 3 factorial is just 3 times 2, or 6. Whoops, now I want my highlighter. But basically, what I'm going to do is I'm going to take NPR, which is the number I got before, 15,600 permutations of those objects. And what ends up happening with this formula is we're going to divide it by 6. And if I go ahead and do that, let's go ahead and see what that gives me. 15,600 divided by 6 leaves me with 2,600 total options. So in this case, the number of groups the teacher could make where the order does not matter, there's actually only, there's only 2,600 unique groups that could be formed, which is only is not the right word to use. But it's significantly less than the number of permutations. And this is another general rule. The number of combinations is always less than the number of permutations, because when order matters, there's way more ways to do it than when order does not matter. And that's another way that might help you be able to remember the difference between these concepts. But the last question is, well, why did I divide it by 6? Why am I dividing by r factorial to get the number of combinations? But actually, if we return back to what I was saying at the very beginning, like thinking about the ways in which order does not matter. So let me kind of rewrite those events, like for example, ABC, ACB. And what I could think about is, what's the difference between order mattering and order not mattering? But if I was to look at all the permutations of those letters, so in the terms of 3 letters, where if the order mattered, these would be 6 different selections for class president. But if I'm thinking about them as groups, this would be all the ways of permuting the group. So like this would be considered as one unique group in the context of a combination, right? Because all of these groups are identical when the order does not matter. But notice that the reduction is 6 to 1, because there were 6 permutations of 3 objects. Because really, there's 3 objects, 3 choices R. So that's kind of the r factorial in the formula. And I want to divide by r factorial because I want to divide out, those are like the excess amount of groups. Because in doing a permutation calculation here, this is all of the ways of doing every one of those objects uniquely speaking. But basically there's a bunch of duplicates, and there's always going to be r factorial duplicates when I'm choosing this amount. And that's why it's always stemming from the secondary number, because that's how many I'm choosing, and that's how many permutations we want to basically throw out. So anyways, like this is all kind of complicated, and this is how I remember all these things. But basically, if you're trying to set up a combination formula, it's always going to be this factorial divided by the difference factorial divided by this factorial, and that will basically, how I remember it is, it will cut out the extras by dividing by the r factorial.